I tried to cover a little bit of ground in this presentation because I've gotten some questions from various channels in this whole project. I know there's some information that several different parties here are interested in. Get participants out of here. So I tried to cover some ground, and we'll just kind of veer off as we need to if there are questions. Essentially what I'm going to cover in this fairly brief presentation is some of the efforts we've been up to for the last few weeks in standardizing the pipeline. Talk a little bit about some of the tools we've developed to try to meet some of the standards we're talking about with the metadata and the data set structuring and all that moving towards the data release. Talk a little bit about the full field stitching, which has been another effort that's been driving sort of a number of other extractors leading into this plot level phenotypes that we're talking about. So I want to talk a little bit about what we've done there and show some images, and then give you some updates on the extractors and where we're at in terms of logging QA/QC for the extractor pipeline, and then just a little bit about the website updates. So this, I kind of cheated a little bit here and just put an image of the TERRA REF poster that we came up with a couple months ago. This will not be anything new to most of you, but I'm going to return to the slide in a minute just to show you kind of where we've implemented some of this in terms of our improvements. So I'm not going to spend any time on this unless you guys have questions about it. The standard pipeline that we've been implementing. So we had this kind of recurring issue or something that we knew that needed to happen where we had essentially the same code written different ways in different places. We had extractors that were doing similar conversions to image formats like geotiffs that were writing their metadata in particular ways, extracting the geospatial metadata from the JSON files that we have on the LemnaText system, and sort of writing the metadata, preparing things for BettyDB. We had this same kind of patterns in the code repeating multiple times. So what we did is implement this TERRA utils library. Can you guys mute? Somebody's not muted. I'm hearing myself. Thank you. So I've implemented this TERRA utils library. You can see it in GitHub there. This is essentially a shared library like PyClouder, if you're familiar with that from some of the work that you guys have done, that's going to be used across our different extractors and scripts in the TERRA REF project. And the idea is that when we have code that interfaces with things like BettyDB or needs to translate from some raw metadata to some standardized format for our project, this TERRA utils library is meant to provide endpoints to let you do that. So you can kind of see in this slide here, I say that TERRA utils encapsulates things like fetching data from Clouder, posting and pulling data from BettyDB, converting to fixed metadata, and referencing fixed parameters. You know, some of these extractors have fixed values in them, assumptions about the coordinates at the corner of the field, things like that. So now we kind of have one place where we start to define these, and each extractor code doesn't need to re-implement kind of the same data. An example of this is the metadata. So Craig Willis, he's actually at a BRAPI conference this week, so he couldn't be on this call, but he has been working on the module that's going to clean the metadata. So right now, if you look at the pipeline, you see something like this. We've got from the Scanalyzer system, we've got data files, and we've got metadata JSON files. We transfer via Globus to the endpoint here at NCSA, and we pretty much just extract the contents of that JSON file as is, put that in Clouder, and then have our extractors trigger on that. This has caused issues at different points in the pipeline in the past when that metadata.json file has changed. The names of fields have changed, or the contents perhaps. We've added or removed fields, and that's caused downstream extractors to break. So the solution that we wanted to move towards is a module that we're implementing in TERRA utils that will essentially pump through the raw metadata before we upload that into the rest of the pipeline. So I won't go into grievous detail here, but you can see on the left some examples of some of the things that we do. So things like renaming metadata to synonyms, standardizing how we do certain operations, like translating to the footprint, the geospatial bounding box of each field, how we fetch information from Betty. And in particular, one of the things that we want to do is get away from repeating the same metadata across every data set. We've got fixed metadata that's essentially on a sensor basis that doesn't really change. Maybe it'll change every year between seasons, if that. But we want to move that data to a place that's visible, that's in Clouder, so that if we need to change a parameter or we realize that something is wrong in our metadata there, we can change it in one place instead of having to change it across 500,000 data sets. And what we'll do is we'll actually have pointers to this canonical reference point for that metadata instead of having it repeated across a lot of different places. There's also some information in the metadata that, at least at this point, we don't anticipate people needing, so we're going to try to be selective on what metadata we carry forward. But the idea is that once we have this module in place, and I have a meeting with Craig once he gets back from his trip next week to figure out how close we are to that. The idea is that we can write our extractors and our scripts against this known metadata structure, and that metadata structure is not going to change ever. We might just need to change the module by which we move from the raw to this known structure. But once we write our extractors against this structure, this clean metadata, we should be much more stable going into the future. So Terra utils is one place where we accumulate all the logic that we need in terms of synonyms and translation and all that stuff. So if we come back to this overall sort of overview of the pipeline here, we've started to implement Terra utils on the upload piece. So the data is coming in from Arizona here at NCSA. We run that through Terra utils cleaning libraries to fetch synonyms, to check BettyDB for plot definitions, to do all the stuff we need to do that's kind of currently done on a per extractor basis or done in a fairly uniform way. We want to implement Terra utils at the extractor level. I spent quite a bit of time going through our existing extractors and replacing their kind of bespoke code with calls to Terra utils whenever we need to generate a geotiff or whenever we need to generate a PNG or do geospatial components. We want to have one function we call, everything goes through the same logic, so we don't have sort of fun character built into our extractors. The last piece that isn't really being used yet, but my goal for Terra utils is also to make it a library that people who are trying to analyze the data can use. So this would be in our analysis tools here at the end of the pipeline when we have the data and you're launching these environments and trying to look at our data. Terra utils is going to provide some usable functions so that you can fetch data more readily, make it a little bit easier to operate without needing to know a whole lot about the underlying sort of interaction between Clowder and Betty. We want to provide simple endpoints that maybe take a simple query, maybe by sensor, date, location, and give you data there. This kind of fits into the search component, which I don't talk a whole lot about in this slide deck, but I'll talk a little bit about that at the end. But essentially, we want to try to standardize all this stuff, and Terra utils was the most immediate way to do that and actually apply some of these standards. I will step back and say that up to this point, we've largely been doing this with a small group of us here at NCSA. David, Craig, myself, a couple others have had a few meetings on how best to do this metadata translation, how to standardize things. I think we've got a pretty reasonable framework in place, but we are going to be asking for input from the rest of the group here on the call in terms of making sure that the standards we choose make sense, making sure that it's cohesive with the kind of the end goals of what we're trying to do with this data. So I don't want this obviously to be unilateral decisions. That said, given the nature of the project and how many people we have and how many moving parts there are, we did decide to just try to keep the ball moving here based on what we thought was the most sensible approach and sort of ask for input as we go as opposed to needing to have whole design documents and lots of meetings before we actually start to get this implemented. So another example that we're going to segue into kind of some images to look at is full field stitching. This has been kind of a bear of a task for this whole pipeline. And just for those of you who aren't too plugged into this whole idea, the vision that we have is that we've got several thousand captures per day. We pump that through the pipeline just like we were just showing. We have nice clean metadata, and we want to stitch all the images we capture for a particular day into one large mosaic of the field. So we had extractors that were doing this written for a few individual sensors. Just as I've been talking about, we tried to combine all those into one shared library that we can pump our data into. And so we have two sensors, the FLIR sensor and the stereo RGB sensor, that have been pumped all the way through this pipeline. You'll see some examples of those in a second. So an example kind of model of what this looks like is that if you come in with your clean data, fresh off the Scanalyzer, we want to have the kind of first line of defense extractor prepare for conversion to geotiff. Most of these sensors are spitting out a bin file, a raw file that's not of much use to anybody. So we have extractors that are converting that to a geotiff. For the purposes of Terra utils, that means that we get that bin data and convert it into a pixel array of some kind. Maybe that's a temperature array, maybe it's 3-band RGB, but we convert that to a geotiff. And the idea is that our geotiffs now, because they're all going through the same module in Terra utils, are of a known quantity. If we write scripts to mosaic the geotiffs together, they ought to work regardless of what sensor we're talking about because we generate our geotiffs in a uniform manner. So we generate these geotiffs as we go. For an example, the stereo RGB camera might generate 8,000 images per day as we scan the entire field. So we have a little module that's generating geotiffs from each of those captures and checking the total number of geotiffs that we have. Once we are confident that we have all 8,000 geotiffs generated for that day, we can go ahead and stitch them together. The stitching involves generating a VRT, which is, I don't actually know what it stands for, but it's sort of a virtual geotiff. It's essentially a text file, an XML file, with a list of pointers to a bunch of geotiffs. So we generate this VRT file, which tells us all 8,000 of the geotiffs that we have and how they're arranged in the field. And from there, we can convert those to a full field image, a geotiff. So if you look on the Roger file system, you will see on level 1, there's a full field directory, and it's arranged by date. Within each of those dates, we have one or more full field images. These images can get big. For the stereo RGB at full resolution, it's about a 100 gigabyte image for one day for 8,000. So we're going to generate two different resolutions. We're going to generate the full resolution, which is going to be massive, and probably people don't want to necessarily download and start to try to open up an ArcGIS because it won't work. But we're also going to generate a thumbnail. So right now I've been generating these at 10% resolution, which is about a 1 gigabyte file instead of 100. So those are going to be used for kind of QA/QC type if you just want to download and take a look at the full field for a few different days, look at a time series. We want to have those available for people who don't necessarily have the horsepower to deal with a 100 gigabyte geotiff. So just to show you a couple examples before we move on here, these are two of our full field images from the last couple weeks. I believe these are both from the week of May 22nd. On the top is the stereo RGB 3-band image. It looks just like a photograph. And on the bottom is the infrared image, single-band temperature reflectance. If we zoom in a little bit, you can start to see a little bit of how these mosaics are generated. I mentioned the 8,000 images. Especially on the FLIR, if you look on the right, you'll see some of those lines indicating where these things are tiled. So this is sort of a medium zoom. We zoom in a little bit more, and you can actually see the individual image captures here. On the left, our stitching algorithm is kind of a work in progress. I'll talk about that in a second. But even kind of our first cut, what I would lovingly call kind of a stupid stitching algorithm, just takes a very straightforward GDAL mosaic tool. We're ending up with a reasonable geolocation there. And so Zong Yang and some of the other group there have been working on improving this algorithm. I'll show an example of that in a second. But I wanted to show this just as an example of kind of the complexity of this problem, right? As this thing moves across the field, the leaves are blown in the wind, positions are going to change. Don't expect to see an image that looks like you just took a super high-res photo of the field at one point in time, because there are going to be these artifacts, noise from the environment, all that stuff. Just to zoom in a little further so you can see there, depending on where the scanalyzer was at the time, there's sun reflectance, and you can see sort of the shade from the gantry there overlaying in different ways. But at least as a first cut, we're seeing fairly reasonable results. We're still kind of realizing what it's going to mean to process against this full field image when you have it. So I wanted to show this. I don't think Zong Yang's on the call. Robert, I think you're on the call. But one of the things we noticed when we first looked at this full field image is that there's sunlight, and because this field takes a few hours to scan, the sun moves as you scan across the field. And here you can kind of see on the left versus the right side of that stereotop image, the sun is getting a lot brighter on the left side of that image. Actually, so I've rotated these to the right 90 degrees. The right-hand side of the image should be north. So at the south end of the field here, the sun has moved. It's no longer being shadowed by the gantry arms so much, so you've got a lot more sunlight on the field. So we realized that we wanted to try to address this so you didn't have these extremely harsh kind of boundaries between the shaded and the unshaded pixels. So Zong Yang went back with their group and started to look at shade correction, and what we have on the right is the current progress compared to what we have on the left. If you look on the left, you'll see that repeated sort of pattern from the shadow of the sunlight in the bottom left corner. You can kind of see the corner of something blocking a little bit of light there and just letting a little bit of light through. What we're going to try to do is essentially take the darker pixel when two pixels are overlaid, and I think on the right is an indication of where we're headed with this. These are just kind of preliminary results, but they've already been much improved. And so I'm hoping in the next week or two we can deploy the latest code to generate mosaics that look on the right a little bit more comprehensive there. But we're encouraged by the results we have so far. And so right now I've kind of generated a few of these full field images for our team to review, and the kind of GIS experts are reviewing. I think we're going to have some tweaks to improve the algorithm before we really start to unleash this in terms of generating a full image every single day. Just for reference, the stereotop takes about 8 hours to generate the full resolution full field stitch. FLIR IR is quite a bit coarser, so that only takes about an hour. But we are going to start generating these, and if you want to look at these, people are sending me messages, emails, and Slack just saying, hey, can you generate this day for me? That's perfectly fine. Just know that if you go on there right now, you will not see every single day being generated because we're still sort of putting the final touches on before we set that loose. So there's a few FLIR and a few stereotop images to look at there, and we're going to continue to evaluate kind of going forward. So, Nadia mentioned early on here that the goal for all this is to get to plot-level phenotypes, plot-level information. And you guys are probably wondering, we're looking at some full field stuff, how do I get to my plots? We talked a lot about this at NCSA, the best way to do this computationally and sort of efficiently. So the two options were essentially generate an image for every single plot for every single day for every sensor, where we would generate this full field thing, which we know we had to have as a reference. We have to maintain a full field image, and then go through and basically cookie cut every single plot out. And we'd have to do that whenever the plot definitions change for whatever season is appropriate. That's still kind of the fallback option if we're not seeing performance that we need, but we're going to try to do this on a on-demand basis first with an API. So the idea here is going to be that the CyberJS team here at NCSA showed us a prototype of this last Thursday. I'm not ready to show it to you guys here. But the idea is going to be that you'll basically have an API endpoint that an extractor can hit to say, for this sensor, for this day, I want this plot. And that plot can be defined by the name of the plot or potentially by an experiment name and a location. Whatever means make the most sense to the scientists in this pipeline, we want to make that supported so that you can basically on demand say, I want this plot for this week for this sensor. And we could go to that API and return you back 5 temporary images. Those could just be an image in memory or a file that's on disk temporarily. We're still working out the specific details. But the idea is that we're basically going to generate these plot images as needed. And the idea is that you can generate the thumbnail version or the full resolution depending on what you need to do. Part of our hope is that for things like the search interface, we can use this 10% low resolution thumbnail of the full field and very quickly query plot level images of that to do things like time series, where you might pick a plot and a sensor and be able to move that time slider left and right and actually see that plot image change over time. So we're pretty optimistic that that's going to be something we can do without much trouble. Given the scale that we're talking about, there's always caveats to be aware of, so we're in the testing phase for that. But that's going to be the vision, is that we can serve these things up kind of as an on-demand basis. And not just by plots, but in theory, we're going to support just an arbitrary polygon. Give me this polygon for this day for this sensor. And this will make it easier to kind of expand this out when the subsequent seasons occur and we have new plot definitions. We just pump those into BettyDB and we can get that all dynamically. Part of what we're thinking here is that we avoid flooding the file system with millions of files per day of each individual plot. But again, we're going to continue to evaluate how well we can get this to perform. So getting away from the full field stitching specifically and talking more about the extractor pipeline, I kind of alluded to the fact that we had spent a lot of time in the last 3 or 4 weeks doing a little bit of a broad improvement of the extractor pipeline. Up until recently, the extractors had been largely a kind of a manual affair. I was juggling these different virtual machines that each had a few extractors deployed on them, and because we hadn't had time to kind of bulletproof everything when the Cloudr instance would go down or when we'd have internet connectivity problems for a moment, it would make the extractors crash and I'd have to go out there and start them up. And it was all this effort that we knew wasn't going to be sustainable. So what I did across the board was to write Docker files, and I'm not sure how familiar everyone is with Docker, but I'm just going to skim over it a little bit here. Docker is essentially a containerization service that lets us push Docker containers, you can almost think of them as little VMs, pre-configured with our extractors and their dependencies and their software. In the same way that you can push things out to GitHub and pull them from GitHub, here you can push images out to Docker Hub and pull them. So I basically cleaned up all of our extractors, generated these Docker files. And you can see I've kind of named them by what type of data they operate on and some unique name on the far right there. So the first one in the upper left here is the FLIR raw data to GeoTIFF converter. By deploying these with Docker, we remove a lot of the overhead of maintaining virtual machines that need particular dependencies, and it becomes much easier to deploy multiple instances of these extractors. The vision here is that we're going to have what they call a swarm of these Docker containers. We're going to have a machine that monitors our RabbitMQ messaging bus to determine when particular queues, particular extractors are getting more overloaded, aka we've got a lot of data sets we need to process for this extractor. We recognize that that extractor is getting overloaded. It's going to automatically generate a second, a third, a fourth instance of that extractor to meet the load until we can get back to parity with current time. So that is near getting ready to roll out. I've been working on this in the midst of other things, but the vision here is that as we process the pipeline, and especially coming up this summer as we regenerate everything to create our data product, we'll be able to generate a lot of outputs in a short period of time by essentially scaling massively and launching a bunch of these Docker containers, a bunch of instances of one of these extractors. In terms of the stuff that we see here at MCSA, this is not something that's publicly exposed, but I thought you guys might be curious. What you see when you look at one of these queues that I'm talking about, so up at the top, this is this FLIR extractor. This is essentially a dashboard that tells me how many messages we have in waiting and how many extractors we have processing those messages. Down at the bottom, you can see 5 IP addresses listed there. Those are the 5 instances of this extractor I'm running. You can see little graphs indicating how many messages we have. And I had this down for a couple days while I was fixing some things up, so that's why it's a fairly high number of messages here. But we are pumping through the messages fairly quickly. The idea is that I can monitor this to see what extractors are under heavier workloads and try to adjust if we need more extractors. If the extractor is not running efficiently, do we need to revisit the code to see if there are ways we can improve it, and generally try to track this. This is kind of manual, and like I just mentioned before, by deploying this in Docker, I'm trying to get away from really needing to monitor this too much, because we'll have services that automatically monitor this and scale up and down as we need to. But this is kind of the under the hood vision there. Another, alongside the Docker updates, we wanted to try to standardize the formats that the extractors are using. Okay, so I talked about Terra utils already. One of the modules in Terra utils is changing the file names and the file output directories. We had extractors that kind of did their own thing in terms of where they were writing their outputs and how they were naming the files. Nobody liked that, obviously, so here's kind of what we're moving toward. On the top half of this, you can see the directory format. Nothing surprising here. We've got the raw data, which most of you have probably seen already, raw data, sensor, the date, and then the specific timestamp, and then your data. So we have some extractors, like in the second line here, that replicate that. We have new outputs for every single timestamp. You know, every couple seconds we're going to have a new data set. But there are others that get aggregated up to the day. So that last directory listing there for the full field, we don't have timestamps for the full field because it doesn't make any sense. We have one image for one day. So you have full field, and then your date, and then some set of images. So the basics for the directory format is that you're going to have some level 1, level 2 raw data, and then we're going to have some interstitial folder indicating what the extractor is or what the data set is. This is still a little bit fuzzy. We're trying to standardize these as best we can. But you'll see things like FLIR to TIFF, full field. Generally, those correspond to extractors. On the file name format down at the bottom, one of the charges we had was to try to make the files operate better outside of the project infrastructure. So if you downloaded one of these files and put it on a USB and walked off, how could you figure out where that file came from? And as many of you probably saw, up until recently, those were just big old hashtag gibberish names with TIFF at the end. And you'd kind of be SOL if you were trying to figure out where that thing came from after the fact. So we try to take inspiration from Modis and some of the ways that NASA and USGS do their file naming formats. And we currently are planning on something like you see below here. So we have the sensor name, we have what level data it is, the date and the timestamp if available, which site the data is from, and then some set of optional, I'll call them flags at the end of the file name. So for the FLIR IR camera, it's level 1 data. That's the day it's from. It's FLIR IR from the UA Max sensor, and it's a PNG file. Stereo top is essentially the same. If you look at the end, you can see _right. That's one of my optional flags. For each stereotop data set, you'd have a right and a left geotiff. So the extractors can still have freedom to kind of, but those flags can be whatever you want. So they can have fairly specific names, but the idea is that you can get this file name absent any other information and trace that back to the data set it came from in Clouder. This is by no means the final format. You know, if we get input from others on the team that we're missing this or this is not going to work, we're certainly open to that. But this is sort of our first attempt at trying to capture all the information that we can to try to make this a little bit more standalone. And so I'll just step back again and say, as many of you are aware, we've been making a lot of these changes kind of midstream with the idea that this summer we're going to process everything, all the raw data we have from square one, generate a full new set of outputs in the level 1, level 2 directories, and have uniformity across the entire time period 2016-2017. We haven't done that yet, so if you go and look at, for example, the FLIR IR camera outputs, the last couple of weeks they're pretty consistent, but if you look back in 2016, 2017, you won't see these file names. You'll see different file names. You might see different folder names. It's been an organic process. Don't be alarmed. That's all going to go away when we reprocess everything, but we didn't really want to spend a lot of time trying to clean things up as we went because we knew that that was going to happen ultimately at the end. But this is the kind of the standardized format that we're going to try to move towards. In terms of the extractors themselves, I know that I had some specific questions on this in the last day. So I've grouped these by what type of sensor, essentially, or what family of sensors we have. The extractors that are in blue are pushing to BettyDB. We have traits pushing those out. The canopy cover and the plant height have been running for a while now. The extractors that are in red were recently delivered by Solmaz. I have converted those to a Docker file and got the Docker file to build, but because of some other issues going on last week, I have not had a chance to deploy these yet. I know a lot of folks are really eager to see those, and Solmaz, I'll apologize to you again that I don't have those deployed. I'm hoping in the next day or two we get those out there and we start to see outputs. But as far as I could tell, the code should be ready to go. I just haven't had a chance to do that yet. But we do have most of these other ones deployed and running, and this segues into QA/QC and logging, another topic of intense interest to many folks, and we've been sort of sprinting to get this in place now that we've got the immediate fires of actually getting the components up and running. So I need to talk to JD. JD set this up based on some databases that I've written for him. I need to check to see if this is publicly available, this dashboard. We've set up a dashboard that lets us view graphs of some of this information about the pipeline health and the extractor operation. So just to show you a couple examples here of the type of information we're trying to visualize, here's the daily pipeline activity. So the two graphs in the upper left, CO2 sensor, you can see the number of files and the number of bytes it's generating per day. We have some hiccups if I paused the pipeline and we had to catch up on multiple days or that type of thing. But generally speaking, we can use this to track how many files are being generated daily, how many bytes are being generated, try to see if there's outliers or if there's dead zones in the data. So this is just kind of the data that's being processed via Globus. We can also see the data sets that are being loaded into Clouder. So this is essentially data that's landing here at NCSA. I'm catching it, I'm uploading it. Same deal here. We can monitor this to make sure that our data is actually getting into the Clouder system and thus triggering the subsequent extractor pipeline. The extractors themselves, I think this is one of the key graphs that a lot of folks are eager to see for their extractors. And like I said, I'm going to talk to JD to see if this is public or not. This is part of the updates that I went through every extractor with TERRA Utils. TERRA Utils now has a module that can write a little piece of data to our influx database, and that piece of data is my extractor for each run, how long it took, the number of files it generated, and the size of the files it generated. Okay, so if we look at these three graphs, these are two extractors with three graphs each. On the left-hand two, we can see the amount of time on average that the extractor took to run. So for the stereotop on the bottom left there, it's usually between 5 and 10 seconds with a couple outliers taking a little bit longer. You can see the data size there. You know, as expected, these are very consistent just because we're dealing with the same data. It's essentially the same image capture. But the size of the data the extractor came out with, and then what essentially should be a flat line for almost every extractor is the number of files it generated. You know, by nature, almost every extractor just generates the same number of files every time. So it should be a flat line, but again, if we start to see variation in these, it's very easy to see what time things started occurring and go from there. So this is our general monitoring dashboard. We're going to try to be improving on this, but when everything's running, we're going to have these charts for every extractor to verify that they're running, see how much they're generating, and see whether they're starting to slow down any issues with the extractors there. we have a error queue where if there are problems with an extractor and it tries to process the data set and it fails, it'll retry a few times. Once it reaches the maximum number of retries, it goes into a big pile of error messages that we have, and we can evaluate what the error was, resubmit those later. So there should be no loss of data, no sort of loss of information if we have to go back and revisit any of these extractors kind of midstream. This last little piece, JD sort of set up just because it was for free with the other database we have, so people might think this is cool down the road. This is a map of who's getting our data via Globus. Not much for me to parse here. You know, you can see some of the obvious spots and maybe some places that aren't obvious, but this could be interesting as we go public to see what folks are downloading the data from where. So this is the last slide. Rachel, I guess I'd ask if you wanted to cover this one. I can try, but it's my first time seeing the slide, so I'll see if you want to cover it.
I'll cover it, but why don't you go ahead and take questions, and then we can move on.
Okay. So let me jump to the last slide first. And in red, this is the last thing I wanted to be sure to mention. If you guys have used Clowder in the past and you've tried to look at spaces and collections, it's been really slow, taking like 30 seconds. I feel your pain. I spent a couple days last week trying to track down every little slow query and inefficiency I could find. Pushed out the results. It's way faster now. You can actually browse Clowder in a fairly pleasant way. So if you've been frustrated by that in the past, do revisit it because it's a little better now. So before we go into the website, I just vomited a lot of stuff on you guys. I'm sure there are questions. What questions do you have?
Max, this is Jeff White. First, very, very nice. It's great to see the progress. I have a few sort of minor detail questions. I guess one is on the metadata. I know there's been cases where we realized later that the metadata hadn't been updated, so it's actually incorrect. So I'm wondering if we have a process in place to retrospectively verify that the metadata are correct.
So yeah, we've talked a bit about that, and our general thought for that pipeline is this metadata workflow. So the idea is that these metadata.json files, some of them, I mean, most of them we trust. We know that some of them in the past have had issues. So this TERRA utils library that's going to be doing the cleaning, each sensor is going to have some set of logic that corresponds to its metadata that says we're going to keep this bit, we're going to toss this bit, we're going to rename these fields. Within those modules, we could add any, for these 3 months there was a problem with the data set, so we need to inject this, or we need to rename this, or we need to flag this as incorrect. That would be the place that we can start to list that information. And we're also going to have kind of a verification step that we can add things like, is this value within this sort of sensible range? And if we have a reflectance that's 9999, maybe we flag that somehow. That's going to be the place where we try to both clean things up, to put any logic for particular kind of, in the past what we've done is hand fixes. Instead we want to codify that here, with the idea that, okay, next year we're going to reprocess all this. We can go all the way back to the raw metadata files and reprocess everything from scratch. And as long as they all go through this cleaning module, anything that we've caught that needs to be addressed can go in there. So that's kind of the current thinking. What we want to avoid, or what I'd like to avoid personally, is to change the raw data around. In the past we've seen that there are issues with some of the metadata, and we've wanted to go run scripts on the metadata JSON files to change them. And I think that might still be unavoidable in certain situations, but if possible, if that's something that we can reflect in our cleaning pipeline instead of trying to go back and change raw files, which makes all of us a little bit anxious, I think that would be the ideal way to do it.
Yeah, sounds good. Another question I have is, if you look at the FLIR images that you've stitched together, there's some quite large looking transitions. Yeah, when you zoom in, yeah, there, okay, perfect.
Yeah,
this may be a sign, I mean, just to see that we're getting data is good, but that looks like huge differences in temperature.
Yeah, and that at that point I would say, we just in the last week started getting these stitches, and so we're kind of at the phase where the experts are starting to take a look at this and evaluate, and we'll probably have some feedback. I don't really have much of a comment beyond there are some files that I can point everyone to so folks can start to look at it. But yeah, we've focused a bit on improving the stitching based on the stereo RGB on the left because that was the first stitching product that we were generating. The FLIR is fairly new, and Nadia, I know you had actually been asking me to generate some of those for your team. Yeah, so I'm eager for people to look at that and let's figure out what we think of it, but that's where we're at right now.
Yeah, for the general group, is there somebody who's going to sink their teeth into this?
So this is Robert. I think when we look at some of these things, the stitching is an important piece to get a global sense of what kind of data there is. When you actually evaluate or run algorithms on this data, sometimes the algorithms will have to use more of the geometry of where the sensor was and how it was acquired than just this like splat it all down onto a flat plane picture.
Yeah.
So I think part of the reason, say, in this FLIR image that's up, that there's such a difference in color is that sometimes the FLIR is maybe affected by, say, direct illumination effects. And so the edge of one image might be have that direct illumination, but the next image is sort of looking at that same place from a very different perspective. As we build the algorithms that actually use this data, we'll be able to take that into account more explicitly than is being done as you build these stitches right now.
Okay. Good. Thank you. Then the last one, as long as we're on stitching, and Stuart may need to provide more insights into this, but I think to speed things up, we're actually skipping quite a bit of territory in some of the scans. So you'll be able to do a full field, you'll be able to generate a full field image sort of in quotation marks, but it's going to have some gaps in it. Is that going to be an issue? Because I think really what we're talking about is just extracting the features from the center of each plot.
So that shouldn't be an issue if I understand your question correctly. Let me try and show you here what I was looking at. So we do have already a couple, like this I imagine is what you're talking about, and this I actually ran this stitch before I had all the images ready. But we do, right now when I do the full field stitch, I basically give it the output footprint. And so if we don't have full coverage for a day, it's going to try to align it with this full image that we have, but it's only going to fill in the data that we have. And so, you know, if we only have a partial field coverage, you'll only see the partial coverage, but what we do have should still align with the corresponding things. I think that should be addressed if that's what you're asking about.
Well, no, what this is more like is, let's say that to do one east-west range would take 5 scans to cover it completely. Then I think Stuart's set it up to speed things up so that, say, we only do 3 scans down the middle of the plot. So what you'd have is good data, a black strip, good data, a black strip.
I would think that should be fine. You know, we'll stitch together whatever georeference data we have, and if there are black strips,
that's the way it is.
There should be no issue. Yeah, that's just what it is.
Once again, I just want to say I'm amazed to see the progress. This looks very good, and my sincere congratulations to your team.
Oh, glad to hear it.
I am glad to hear about the alleyways not being an issue, because I have been intentionally still giving you basically data there in that like 50 centimeter area where there aren't any plants, because I didn't know if that would be a stitching issue down the road. So
no, yeah, fortunately each image is georeferenced essentially independently of everything else, and so we'll just stitch what we have for that day, and there might be gaps, but that should be no issue.
All right, well, I will hack out that extra 50 centimeters as soon as I can here then.
That's actually an interesting conversation we had, just because when we were talking about that full field image versus clipping to the plots, you know, we kind of talked about, is there value in the data between those plots? Is anybody ever going to look at those pixels if it's not in one of our experimental plot boundaries? And for now, for the moment, we're going to keep that full field image, so we're not going to discard that information. But, you know, I did wonder if down the road, a couple years down the road, we start to worry about how much data we're accumulating, we could think about only storing the plot level imagery. But yeah, whatever we have is what we have, and it should all be fine.
I did have another question. What do like turnaround times look on things like this?
So I'll give you a multi-part answer for that.
Of course.
There's a turnaround time absent. If we started up the pipeline right this second and you started sending the very first data, the turnaround time is pretty good. We transfer the data within about 10-15 minutes of when it lands on the FTP server. We get the extractors processing the raw data. That takes, as you saw, maybe 20-30 seconds. And then once we process the full day, so assuming that we wait until that night or the next day for the full scan to complete, generation of these full field images takes about an hour for the FLIR camera, and at most 8 hours for the stereo camera for the full field image, but for the 10% thumbnail resolution, that's about 45 minutes. So if we kind of take all that into consideration, my hope is that after we run the scan, 48 hours is our target time, but if things are operating smoothly, I would hope, by mid-morning the next morning we start to have results. The longest one is the stereo RGB, and I guess I'd say the biggest issue that we wrestled with here at NCSA is what's that magic rule that tells us we've got all the images for a day? Generally speaking, if we wait until the next morning, we've transferred most of the data, but not always. Sometimes there's a few straggler files that arrive within the next 48 hours or so. So up until this point, we've been operating on a 2-day rule, where if it's Wednesday, I'm going to go and start processing Monday because we're pretty sure we've got all Monday's dates. But we're still trying to improve some of the logic we have there to make sure, based on the file transfer patterns we're seeing, that we're not overlooking files. And I think the 40-hour window is probably more generous than we need to be. But if everything's empty, we can get through this whole process in about 5 hours at most.
That's very good. Okay.
Hi, Max. It's Jeff Morris. Great to see all this coming together like this. I had a question. Robert Pless has talked before about the height measurements being the kind of hello world.
Yeah.
Another hello world that I think we should be thinking about, and I'm wondering whether it might be time, is doing a P to G analysis. Probably on the plant height, just to show that we can, as a team, can make that whole connection. So I guess my question is, do you think we're close, and what do you need from my team or others to help make that happen?
Well, I would say we do have some plant height traits. We have an extractor that's been running with some of that information. The next step I would say is why don't we make an issue in GitHub that we can take this discussion. What I would do is probably share with you the data that this plant height extractor in blue there is spitting out. Solmaz has also got this 2D height map extractor that she's waiting on me to deploy. So we're going to have two sources of information that are coming online. One of them's already online. The first thing I would do is give you some of that information, say, here's what we have right now. I'll share my ignorance here and say I'm a programmer, so I'm not really familiar with a P to G analysis. I want to just, here's the data we have. What data do you have? What can I give you?
Yeah.
But I think that would be the next step. We do have data to share.
Okay. So when you set that up, put Zhen Bin on that. He'll
Okay.
be actually doing that. And I'm sorry, I was using jargon. Yeah, just connecting the phenotypes to the...
Phenotype, genotype. I'm learning some of that stuff.
Sure, yeah. So,
Yeah, I'll make a GitHub issue. I'll tag you in it, and then we can just see if we have enough data to get that going there.
Mm-hmm.
I think we might in Betty, though.
Perfect. Thanks.
Okay, thanks, Max. Unless there's some really burning questions, I really want to take the next few minutes, maybe let Rachel talk about the updates to the TERRA REF website. We definitely need feedback from the group as to kind of what we need to work on. So, Rachel?
Great, thanks, Nadia. So I'm Rachel Shaker. I'm the project manager with